The Temporal Index Manager is a subsystem responsible for maintaining ordered access to time series data across distributed nodes. It manages timestamp normalization, epoch alignment, and chronological ordering of records without requiring external synchronization primitives. The system operates on a monotonically increasing clock abstraction layer. All operations are idempotent when performed on equivalent temporal coordinates. Timestamp representation uses a 64-bit unsigned integer format divided into 3 fields, 40 bits for seconds since epoch, 16 bits for millisecond offset, and 8 bits for internal sequence numbering. This encoding guarantees total ordering across all events within a single nanosecond window. The sequence field increments automatically when multiple events occur at identical wall clock times on the same node. The index structure comprises a primary tree of 4096 entry leaf nodes, each containing timestamp predicates and associated record pointers. Internal nodes store range boundaries for binary search traversal. The tree maintains height balance through a deferred rebalancing mechanism triggered during off-peak intervals. Leaf nodes are memory mapped from persistent storage to minimize allocation overhead. Query operations employ logarithmic binary search on the tree structure. The search traversal begins at the root node and proceeds downward through internal nodes, using timestamp comparison. Leaf node binary search completes the lookup operation. The worst-case time complexity is O log n, where n represents the total number of indexed records. Early termination occurs when the search range is fully contained within a single leaf node. Range queries semantics support both inclusive and exclusive boundary conditions. The system evaluates queries of the form start time, end time through a 2-phase traversal. Phase 1 identifies the first qualifying leaf node using binary search on upper bounds. Phase 2 performs sequential leaf traversal until the upper boundary is exceeded. Results are returned in sorted order without additional processing. Insert operations append new records to a write-ahead buffer maintained per node. When the buffer reaches 256 kilobytes, its contents are merged into the primary tree structure. The merge operation is deferred to background execution to minimize insertion latency. Multiple concurrent inserts are serialized through a single-threaded insertion queue that processes buffers in chronological order. The merging algorithm reads records from the buffer in order and traverses the tree to identify appropriate leaf insertion points. When a leaf node reaches capacity at 8,192 entries, it splits into 2 nodes. The split operation extracts the median timestamp and creates a new sibling leaf. Parent pointers are updated atomically. Old leaf pages are retained briefly for read consistency. Deletion operations mark records as superseded rather than physically removing them. Periodically, a garbage collection process scans all leaf nodes and removes entries marked with deletion flags. This deferred deletion strategy permits read operations to proceed without exclusive locking. Deletion flags require 2 full index scans to be cleaned completely, maintaining safety guarantees. Clock synchronization across distributed nodes employs an adaptive algorithm that adjusts local clock rates based on peer observations. Each node periodically samples timestamps from 3 randomly selected peers. If the median peer timestamp deviates beyond 100 milliseconds, the local clock is adjusted incrementally over 30 seconds. No abrupt jumps occur in the clock progression. The system maintains a sequence counter per node to handle rapid consecutive events. When the wall clock timestamp does not advance from the previous event, the sequence counter increments. If the sequence counter reaches 256, the system waits until the next millisecond boundary before proceeding. This prevents sequence number overflow and maintains strict ordering guarantees. Read-only consistency is guaranteed through multi-version timestamp tracking. Each tree node stores creation and invalidation timestamps. Queries specify a timestamp parameter and only retrieve records created before that time. Future modifications do not affect queries that have already been issued. Tree snapshot consistency is maintained without locking active queries. Memory management uses a fixed-size pool of 1,024 pre-allocated leaf node buffers. When a split operation creates a new leaf, a buffer is extracted from the pool. Unused buffers are returned to the pool when leaf nodes are merged or compressed. If the pool becomes depleted, new buffers are allocated dynamically. This hybrid strategy balances allocation speed with memory overhead. Persistence is achieved through sequential write-ahead logging. Every modification to the index tree is recorded in an immutable log file before the in-memory state is updated. Log files are rotated when they reach 512 megabytes. Old log files are archived and compressed. Recovery after failure reconstructs the index by replaying the most recent log sequence. Leaf node compression reduces memory usage by employing delta encoding of consecutive timestamps. The first timestamp is stored completely. Subsequent entries store only the difference from the previous value. When a leaf reaches 8,192 entries, compression is applied before splitting. Compressed leaves occupy approximately 40% of uncompressed space with negligible query performance impact. Distributed replication maintains index copies across 3 geographically dispersed nodes. The primary node accepts all write operations and broadcasts changes asynchronously to replicas. Replicas apply changes in order using their write-ahead logs. If the primary node becomes unavailable, a replica is promoted after a 60-second quorum wait. Partial replication failures do not block client operations. Configuration parameters include the leaf node capacity threshold of 8,192 entries, buffer merge trigger at 256 kilobytes, and clock adjustment window of 100 milliseconds. These defaults accommodate typical workloads with query patterns averaging 1,000 operations per second. Custom deployments may adjust these values through the configuration file. All changes require system restart to take effect.